Okay, so it's working, I think, I hope. Let me see. I want to see the mic working. Not working? No, not so sure. I think it's working, right? I think this indicator changed, so I got confused. So the mic is working. Then now we finished this spectral representation on page 62. So we go ahead. The extreme value of the strain tensor E and small e and their directions, principal strains and principal directions, are related to the principal stretches and their directions in a simple fashion. In the eigenvalue problem, something equals something, 0, this is just the same eigenvalue. Okay, I skipped it. The analysis, okay, sorry, we start from here. Yeah, because in the last video we finished up to here, right? The analysis of the material ellipsoid. Now we talked about spatial ellipsoid up to here. So now we are talking about excuse me, material ellipsoid. Okay, Gij dxi dxj equal k square can be carried out in a similar manner. Okay, eigenvalue of small g will be denoted by 1 over excuse me, 1 over lambda square, small lambda square I, and the eigenvectors by n. It has the spectral representation. Was it correct? I'm not. I have to go back to see. See, this is okay. So I think in this case, now we do this one. G. Yeah, I think this is the origin. We have this one. 551. We have this. See, G. This is eigenvalue. You have eigenvalue like this. How do eigenvalue? Eigenvalue is lambda gamma eigenvalue square 1 over something like this. So this is the eigenvalue. Yeah. So in this case we should use I. ijk instead of alpha, beta, gamma. So anyway, so this is same. This is same thing as G, I. Yeah. Then we have a spectral representation. The extreme value of the strain tensor E and small e and their directions, principal strains and principal direction, are related to principal stretches and their directions in a simple fashion. In the eigenvalue problem, this is exactly the eigenvalue problem we solved above. Actually, I don't know if we have solved it. Anyway, I think in the previous video we solved this eigenvalue problem. Then we obtain spectral representation. Okay, so if we substitute G, this was all the relation we learned. So we substitute something like this. Then we get this way with the delta. Okay. Yeah, I think we get it. Put it here, right? So we have 2 E alpha beta. We have this one from here. N beta, this one from here. Then we have plus. So this minus and minus, then plus. We have delta alpha beta. Then we have beta. So beta is a summation convention. So beta will change to alpha by this delta, Kronecker delta. So you will have 1. You have 10. Then you have alpha. You don't have 1 over 2. Then you have minus. Minus is here. Then there is a G. G gamma, G gamma. The N alpha. So in the end, we just divide everything by 2. So you will have 1 half. So this is correct. So we get this. The principal direction of strain tensor E and are the same as N alpha gamma. And principal strain R. This is like a principal strain strength. Strength. Strength or like value. Principal strain values are something like this. 1 half G gamma minus 1. Similarly, so this is similarly you have change this swap. For small e, you have 1 minus G. 1 minus G. Thus, the solution of the eigenvalue problem for large G or small g also gives the principal strains and their directions. We note that the strain matrix is not positive definite. Okay. Strain matrix is not positive definite, and the term strain ellipsoid will be incorrect. Actually, I'm not quite understand the deep meaning of positive definite. Okay, this just mean all eigenvalues are positive. Yeah, all eigenvalues are positive. This is positive definite. But I'm not completely sure what's mathematical or physical meaning for this, because it seems to me, if you just add some constant diagonal, like large positive values, constant matrix, then it seems okay. I don't know. Okay, anyway, polar decomposition and deformation gradient. The deformation gradient tensor this is interesting. You see, one index is alpha, the other index is I. So this is alpha xi. So this, if you write this out, this goes like partial xi, partial x large x alpha. This is a deformation gradient tensor. Okay, has the property FF transpose equals G, where we have seen G is symmetric and positive definite, but F is neither. F is neither. From the theory of matrices, we know that we can factor any real square matrix into an orthogonal matrix and a positive definite symmetric matrix. We can factor any real square matrix into orthogonal matrix and a positive definite symmetric matrix. Factor, this is like a multiplication. The deformation gradient matrix F can be expressed as F is orthogonal matrix times positive symmetric. R is orthogonal rotation matrix and U is a positive definite symmetric matrix known as the right stretch matrix. The matrix V is called a left stretch matrix. This factorization is called a polar decomposition. As discussed in chapter 2, the orthogonal matrix R satisfies R transpose R equal I, R transpose equal I, R transpose equal R inverse. positive definite symmetric matrix. Right stretch matrix and left stretch matrix. Using these properties from equation 586, we get F transpose F equal U square This is okay. So this is given. This is given above. The question is this one. This is a question. And I think there was a nice summary page. Let me see. Where is it? Somewhere here, right? Somewhere here. See this one. Yeah, this one. So you go alpha alpha. This is summation, ascent. But then this one, this part is ij component. This is the ij component of this matrix. Anyway, so we have this. This is what page? What page is it? 54 page. Page 54, we have this. So we can now accept the formation. I think we have done this. Done this. Okay. So we note I got confused. Was this actually G inverse? Was this G inverse? I think this was G inverse. Like, 54. It's not 54. Strange. Okay. Okay. So this is interesting. So G inverse is G ij. Up. Anyway. We note that eigenvectors n gamma of G are the same as those of V. Why? We note the spectral representation of V is this. G. Interesting. G for G. This is lambda square. Lambda square, right? And spectral decomposition of V is lambda, not square. I'm not so sure, but how come F? Because of this V. V is symmetric, right? V is symmetric, positive definite. Positive definite symmetric matrix. See, V. Very interesting. V. I think we have to say something like this. This is actually a G. G is this, and G inverse. G inverse is this. So G is FF transpose, and which is V square. And for some reason, this has the same form for the spectral decomposition using lambda gamma. In a similar way, we may resolve the Cauchy deformation gradient F as F equal U, RU equal VR, R transpose R equal RR transpose equal I, FT, F transpose F is U square, and I think we had a name for this. Let's see, G. We had a name for this. G. Small g and large G. Large G inverse and small g. Okay. This is large G inverse, and this is small g. And this one, I don't know where we have this. Is it like fi alpha equal partial I large X alpha? Is this the case? Yeah. So here we have learned this one and this one. Yeah. Then okay, here we learned. We have already learned, although I don't remember exactly. So large F times small f is identity. So this is correct. Yeah. So we have VUI. How do you do this? UVI, RI in terms of eigenvalues and eigenvectors of G, lambda 1 over lambda inverse, 1 over lambda, and Ni. This is just a spectrum decomposition. So how do you know this? F is RU, right? See, F is RU, and small f is RU, correct? Small f is RU. So you can do FF is RU, RU equal 1, identity. You can do VR, this is, you can do VR, or you can do RU VR. So this is identity. This is identity. VU is identity. I think this is not proved. Anyway, let me ask Professor now about this one. Let me ask him. He may answer. What equation was it? 591. So move ahead, okay? So next part is a stretch and rotation. In the relation, I'm sorry, I don't even remember if we had this rotation. Using polar decomposition, we get, oh my god, the operations on dx show that in the first case, the mathematical element is rotated by RT and stretched by U. And the second case, it is first stretched by V and then rotated by UT. For arbitrary vector n equal dx slash ds, we obtain something like this. Writing something, we have something like this. Logarithmic strain, change of volume, change of area. Okay, let me see how long. Actually, I have something to do. So how we have done 35 minutes. So let me stop this video here. We continue the next one next time.